Okay, we're going to try something a little different and use Loom to record the lecture for the object-oriented programming. So this lecture is entitled Everything You Wanted to Know About Object-Oriented Programming, but We're Afraid to Ask. And this is for CS151, obviously. So we're going to introduce some constructs or review some constructs from 150, including structs, classes, and namespaces. And I'm going to illustrate these using a program that functions as a faculty advisor for students, and it's based on the Magic 8 Ball, which was a toy that you would shake up and ask questions and would say, things like answer unclear, ask again later, or definitely not, or signs point to yes, different types of things as an oracle. It's probably as good a faculty advisor as I am. So we can start with structures, and in the last lecture we looked at very simple data types, int, double, float, character, etc. And what we can do is we can make composite data types into a collection. So we can put these things together to group them into a entity that has more details. We treat that composite as a whole, but still allow access to the components. So for example, we could have a struct for a student. The student would have a name that was indicated by a string, a GPA indicated by a double, and credits that were indicated by an integer. And whenever we define a struct in C++, we need a semicolon at the end. So we can now use our struct just like a variable or a variable type. So I can say student and give that student a name of advisee that I can refer to it by, and then I use the dot operator to get access to the individual components. We treat the member variables just like any other variable. We can assign it a value, get input, pass it to a function, print it out. So for example, I could get the advisee name using the cn and the extraction operator to get that from the string. We can also use them in assignment statements, pass them as function arguments, and return them as a result of a function. So a related concept is classes. These are a structured data type. They're a data type that we define. They'll be composites of related items, and they may have different types. In fact, they usually do. And we treat the composite as a whole, but still allow access to the individual components. So that's just like a structure, right? Well, not exactly. Classes have member functions that allow them to perform actions, or these are called methods in object-oriented programming. And so this is object-oriented programming proponents say, well, this is a pretty natural view of the world. And what we need to do is say, well, what are the important entities in our problem? What kind of data describes them? What are the natural activities they should be able to do or carry out, and write classes or classes for them. And this is particularly applicable in graphical user interface programming, where you have objects on the screen that correspond to classes. For example, a character, it could have a size in terms of number of pixels that it takes up, and it could perform actions like run or jump to take part in a video game. So when we do object-oriented design, we need to identify the objects that are needed to solve the problem, what data we need to use to describe them, what actions they should perform, and we combine those together along with the variables and the functions into a single package, and that's known as encapsulation. So first of all, we describe or define the member variables, what the objects of the class will look like as far as what data they can have. For a video game character, that might be the size of the character, its color, its position on the screen, and that's done just like a struct definition, except we use the word class instead of struct. And then we define the member functions. These go inside the class in terms of a declaration, but the definitions go at the bottom of the program, or they go in a separate .cpp file that has the same name as the class. And we'll get to that when we talk about separate compilation. So for object-oriented design, identify the objects you need to solve the problem, what data you need to describe them, the member variables, and what actions they should be able to perform. And then we combine those together into the class. So We also have public and private, and later on we'll get to protected. Public members of a class are accessible from anywhere, whereas private members are accessible from only within the class. In general, we want to make the member variables private, but make the member functions public. And in application code, that is, inside main or a regular function, you can't reference a private member variable. You can reference a private member function, or a public member function. That's A-OK, and in fact, that's what we'll do. Within a member function, you can reference member variables that are private. And so in order to get around this problem, we write some different types of functions. One are accessors. These are also known as getters. And these retrieve the value of a member variable for you. You can usually write these as inline functions in the class, assuming that they're just one line. Mutator functions set the value of the member variable for you. And again, you can write these as inline functions, assuming they're just one line. And then constructors, which are basically what we use to generate the objects of the class. They typically have the same name as the class, and you usually have more than one constructor. They're usually separate from the class definition at the top, although it is possible to write them inline as well. So 3 components of a class: the interface, the public member variable declarations. This is the what. The implementation is how we actually do things. Those are the private member variable declarations, all the member function definitions, and those usually go at the bottom or in the class.cpp file, and then the actual use, and that goes into the main application program. So this goes to an idea called abstract data types. A data type is called an abstract data type if the programmers who use the type don't have access to the details of how the values and operations are implemented. And, in fact, you've seen this with the string class in C++, or, even the IO stream, which streams are classes. You probably don't need to know all the details of how CN and Cout work. And so we actually separate our class into separate files. The interface goes in a header file, and that's what the application programmer sees. The use is the application code, and the implementation, which is what we hide, goes into a file that's the same name as our class, but with CPP. And users of the class only need the interface. They need to know what it does, but don't need to know the nitty-gritty details of how it gets accomplished. So, abstract data type is a set of values and operations that we can use to process those values, and it's independent of the implementation. Separate files are good because they hide the details. Once the implementation file is tested and bulletproof, you don't need to compile it again, and this allows us to make reusable code or class libraries. A couple related concepts that are needed are namespaces and overloading. So, overloading was where we gave different signatures to 2 functions with the same name. This is useful for class constructors, so we can have 2 constructors that take different parameters, or where you have partial information that goes into a function. The signature is the function's name along with the sequence of types in its parameter list. And in CS150, we saw how to do this overloading with different signatures. For example, we could have 2 area functions, one that computed the area of a round pizza and one that computed the area of a square pizza. The one for the square pizza or rectangular pizza would take length and width, whereas the round pizza would just need the radius. And we also saw it in classes where constructors take on different information depending upon how much information we want to give when we're initializing the object. What about 2 functions with the same signature? So if you've taken geometry, you may recall there are different types of distance. One of those is the classic Euclidean distance, where distance is equal to the difference of the x and y values squared and taking the square root. And then there's the Manhattan distance, which is basically the difference in the number of blocks that we would have to walk. Here we would need separate namespaces to accomplish this. So we could have a namespace Euclidean and a namespace Manhattan to correspond to the different types of geometry we're using. And then we can use the scope resolution operator to indicate which namespace we're calling from. And some people like to issue using the namespace standard statement and then indicate that they're calling everything from standard. So std : cout. I guess it helps if you're using if you're doing a larger project that has a lot of different namespaces and you're not always sure you want to do things from standard, or if you just like typing std : quite a bit. But for larger projects, it will eventually become a necessity. So when a program uses different classes and functions from different programmers, there's a possibility that two of those programmers are going to use the same name for two different things. And namespaces allow function overloading with the same signature. Otherwise, those two functions would be indistinguishable. So what we do is we put them in different namespaces, and this is important for larger projects. So that's a wrap. Thanks for listening.